Hello learners, my name is Mr. Lola. Once again, welcome to Black Slides Online Secondary School, where you are all welcome to learn the sciences and other subjects on a request for free. And as long as you are learning on this channel, learning on this channel is entirely for free. The only expense that you should meet is to buy yourself enough internet data so that you can learn as many subjects as possible. You can watch as many videos as you can in this channel. But just in case you are interested to learn privately through our private platform, you are free to contact us on the numbers shown here. So without further ado, welcome to today's lesson. This happens to be lesson number 3 of the topic digital electronics. Remember, in the topic number 1, we looked at the basis for digital electronics, which is called the band theory. The band theory. All right? So the band theory is just an assumption that when two atoms are brought closer to each other, their energy levels are going to split into smaller energy levels, and such smaller energy levels are called bands. And there are two types of bands, as we saw in lesson number 1. We have what are called the valence bands and the conduction band. Remember that the valence band is always filled up with electrons, all right? And the conduction band may or may not contain electrons, depending on the type of material. All right? So, based on types of materials, in terms of conductivity of electricity, electrical conductivity, we saw that materials can be insulators, can be semiconductors, and conductors. Where we said that insulators are materials, all materials that do not conduct electricity. All right? They do not conduct electricity for the simple reason, apart from not having free electrons, as we explain in physics sometimes, but the main reason is that between the conduction band and the valence band, there is a very wide gap. This gap, which is called the forbidden gap. All right? Remember that for any material to conduct electricity, all right, the conduction band must have electrons in it. Unfortunately for insulators, there are no such electrons. Okay, electrons in insulators are only found in valence band. Valence band. So there's a gap, very wide gap between the valence band and the conduction band. So the gap prohibits electrons or forbids electrons to jump from the valence band to the conduction band. It is for that reason that insulators do not conduct electricity. Other than that, we have semiconductors. Remember that semiconductors are materials whose conductivity lies midway between insulators and conductors. All right. So the gap between valence band and the conduction band in semiconductors is small, smaller than that of insulators. Therefore, semiconductors allow electrons to jump the small forbidden gap, allows electrons to jump from the valence band through the small forbidden gap to the conduction band, allowing semiconductors to conduct. All right. And we cited examples of semiconductors as silicon and germanium. These are elements belonging to group number 4 of the periodic table. Lastly, we looked at, in lesson 1 still, we looked at conductors, which are the materials which allow electric current to flow through them. In other words, they conduct electric current so easily. Once connected in a circuit, electrons can easily flow through them. Why? Of course, you'd say they have free electrons, but what that means is that there is no forbidden gap between the valence band and the conduction band. In other words, the valence band and the conduction band overlap such that electrons can easily move from the valence band to the conduction band where conduction occurs. All right. Okay, and all metals belong to this particular class of materials. Now, coming back to semiconductors, all right, we looked at semiconductors as having two types, namely intrinsic semiconductors and extrinsic semiconductors. We defined intrinsic semiconductors as pure semiconductors whose conductivity relies only, or whose conductivity can be enhanced by increasing temperature. All right. So an increase in temperature would enhance or improve the conductivity of intrinsic semiconductors. Examples of intrinsic semiconductors are silicon and germanium. When silicon or germanium is heated, the electrons in the valence band gain kinetic energy, enabling them to jump through the small forbidden gap to the conduction band where they are needed to conduct electricity. Right. So the only means to increase the conductivity of intrinsic semiconductors, silicon or germanium, is by raising their temperatures. On the other hand, we have what are called extrinsic semiconductors. All right. These are semiconductors whose conductivity can be improved or enhanced by simply adding small amounts of impurities through a process called doping. And we saw that doping can result into the formation of either N-type semiconductor or P-type semiconductor. All right. Okay. So what type of semiconductor, extrinsic semiconductor you produce depends on the doping elements used. Okay. In order to make silicon or germanium P-type, all right, it must be doped with a trivalent element. A trivalent element is a group 3 element of the periodic table. An example of such an element is boron. Remember that boron, by virtue of its position in the periodic table, group number 3, It means it has 3 electrons in its outermost shell. So when bonding with either silicon, covalently, silicon or germanium, there is going to be a deficiency of electrons to be supplied by boron. Okay, so as a result, boron will develop what is known as a hole or a positive charge carrier, resulting into the formation of a p-type semiconductor, extrinsic semiconductor. On the other hand, in order to form an n-type semiconductor, which is negative in nature, it means that either silicon or germanium should bond, not react, but bond with a pentavalent element, which is a group 5 element, for example, phosphorus. Phosphorus, by virtue of its position in the periodic table, has 5 electrons in its outermost shell. But when bonding with either silicon or germanium, it will utilize only 4 electrons, and 1 electron will remain unbonded. Such an electron is going to be free and available for conduction. All right? Okay, so in today's lesson, which is lesson number 3, we are going to look at the p-n junction diode. The p-n junction diode. So we're going to see what this is in terms of definition. What is a p-n junction diode? And we are going to look at its action. Action in a circuit. When connected to a circuit, how does it behave? Or how does it make electric current behave? All right. So as I've always said, by liking this video and subscribing to the channel, as well as hitting the notification bell, you are going to do yourself a lot of good, because as the videos are uploaded from time to time, lessons, you are going to be the first one to know. All right, so consider subscribing and hitting the notification bell so that you get latest updates, latest videos as they are uploaded. So once again, like, subscribe, and hit the notification bell for you to be kept updated every time when a video or a lesson is uploaded. So welcome to the p-n junction diode. We are going to define the p-n junction diode in the following manner. We define a p-n junction diode as an intrinsic semiconductor. Take note, it is an intrinsic semiconductor which is doped simultaneously by trivalent and pentavalent atoms, such that one half of it becomes p-type and the other becomes n-type. Let me break down this for you. All right, so we are looking at an intrinsic semiconductor, okay, like silicon or germanium. Remember that every time we are mentioning intrinsic semiconductor, we are basically talking about either silicon or germanium, because these are pure semiconductors, and these pure semiconductors are called intrinsic semiconductors. So pick silicon, for example. So silicon can be doped, or some impurities can be added to it. That's what it means by doped, from a process called doping. So is doped simultaneously or at the same time by both trivalent atoms and the pentavalent atoms. Okay, what this means is that one end is doped with the boron, the other end is doped with phosphorus. Okay, so the result is that one end of silicon semiconductor, the intrinsic semiconductor, will become positive and the other end will become negative. So the name given to such an intrinsic semiconductor is PN junction diode, or just a diode. But you have to be particular and specific about which diode we are talking about, because you also have what are called Zener diodes, whose action may be different from the one we are talking about here. All right, so when connecting PN junction diode in a circuit, there are two ways you can do that. All right, so there are two ways of biasing. Biasing is the connecting of the diode, the PN junction diode, in a circuit. All right, so these two ways are forward biasing and the reverse biasing. We are going to explain what this means shortly. All right, so we are saying there are two ways to connect a diode in a circuit: forward biasing, or forward connection, and the reverse connection. So let's look at forward biasing. So the PN junction diode is forward biased, or is connected in a forward bias when the p-type region is connected to the positive terminal of a cell or battery, and the n-type region is connected to the negative terminal of the battery. Then you have connected the diode in a forward biased mode. So positive terminal of it goes to the positive terminal of the battery or cell. For example, shown in this diagram, this is a PN junction diode. It has two ends. One end is positive, the other end is negative. Okay, although I've not shown here labeled properly, the p-type, the p end, the positive end, is what is called the anode, and the n end is what is called the cathode. So the cathode is connected to the negative end, the anode is connected to the positive end. When you have connected like this, then we say that your diode is in a forward biased mode. So when a PN junction diode is forward biased, it allows current to flow only in one direction. In other words, it conducts current in only one direction, such that if you reverse, let's say the negative, the n end is connected to the positive of the cell, and the p end is connected to the negative of the cell, it's not going to conduct. So for it to conduct, the n end should be connected to the negative terminal of the battery or the cell, and the p end should be connected to the positive of the cell. Now the symbol for a diode is the one shown here. Take note that it is inscribed in a circle. All right, so should they ask you to identify it in a circuit, take note that you have this, what looks like a small triangle, and then a vertical line at its tip, and then you inscribe it in a circle. Take note. So this end here is the N end, the negative end, the cathode end, the cathodic terminal of the diode, which is connected to the negative end of the cell. The other end is the anodic or anode end, which is the P end and is connected to the positive terminal of the cell. Such a connection is called forward bias. Forward bias. So in a forward bias mode, the diode is going to allow current to flow through it only in one direction. Remember that when you reverse the terminals, let's say you bring the N end to the positive terminal and the P end to the negative, it is not going to conduct. So P to positive, N to negative. I hope we are together there. All right, so the characteristic for a diode in the forward bias mode is shown in the graph here. All right, the diode is, you can see that this is not a straight line. If you plot a graph of current I versus voltage, you are going to get a curve like that, not a straight line. Okay, this means that at low voltages, the current changes slowly until when the voltage reaches a certain point when the current sharply increases. So the current increases rapidly when the forward bias voltage is increased beyond what is called the cut-in voltage. So this cut-in voltage is a point where the current seems to increase very sharply and very rapidly. All right, so because the graph line is not straight, as you can see here, we say that a diode is non-ohmic conductor. It's a non-ohmic conductor, meaning it does not obey Ohm's law. Remember that Ohm's law says that electric current is directly proportional to the voltage across a component under constant conditions such as temperature and the other factors. All right, so here there is lack of that proportionality. It is some kind of curve, all right, which means that the diode, the PN junction diode, is not an ohmic conductor. It's non-ohmic conductor. Very important. So what we are saying here is that we have a diode, a PN junction diode, which is made up of two terminals, the positive end connected to the positive of the battery or the cell, and the negative end connected to the negative end of the cell. All right, and that diode only conducts electricity only in one direction, meaning that if you swap the terminals, it is not going to conduct. All right, so unless you have questions, feel free, if you have any questions, to contact us or just to leave a comment in the comment section below. Now let's look at the reverse biasing. Remember that there are two ways to connect a diode. You can connect it in a forward biasing mode, in which the P end is connected to the positive of the cell and the N end is connected to the negative of the cell, and that will allow electric current to flow through it only in one direction. So a PN junction diode is said to be reverse biased when the P-type region is connected to the negative terminal of a cell and the N-type region is connected to the positive terminal of a cell. So when a PN junction diode is reverse biased, it offers very high resistance to the flow of electric current. Therefore, it does not allow current to flow. In other words, it does not conduct. I mentioned this in the previous slide that if you reverse the diode such that the N end goes to the positive of the cell and the P end goes to the negative, it is not going to conduct. It will not allow current to flow through. A diode only conducts in one direction. Alright, so using the symbol, electric symbol for diode, this is the circuit showing the reverse biasing of the PN junction diode. So, as reverse bias voltage is increased, there is no significant change in the current until a particular voltage, which is called Zener voltage, when current surge is noted. Alright, so we are saying that when the diode is connected like this, alright, there is never going to be current flowing through until at a certain point at a particular voltage, which is called Zener voltage. That's when you'll be able to see, to note some current surge or a sharp increase in the voltage. Alright, so here we have brought the two connections. This graph is showing us that. So we have current in the forward bias, FB. Current IFB means current in the forward bias, and down here current in the reverse bias mode. Okay. This end we have a graph showing reverse bias, forward bias, in which current increases sharply as voltage is increasing, and we have this end, the reverse bias mode, where current is not noted until a certain voltage, which is called the Zener voltage, when the current is seen to increase or to rise very sharply. Alright, so in case they ask you to sketch these graphs for both connections, take note of the shape of the graphs. My name once again is Mr. Chilola, and I would love you to be flexible and feel free, if you have any questions, to forward the questions to us. We'll be able to attend to you. Remember again to like, subscribe, and to hit the notification bell so that you don't miss any videos as they are being uploaded. Alright, now let's look at some use of diodes in practical circuits as examples. Alright, example number 1 is saying the diagram below shows a circuit with two diodes D1 and D2. So we have D1 here and D2. Take note of how they are connected. Two lamps, L1 and L2. We have lamp 1, lamp 2, and a battery. State and explain the observations that would be made when the switch S is closed. Alright, so we have a switch over here. So what I want you to pay attention to is the connection of the two diodes, how the two diodes are connected. Let's follow diode 1. If you follow diode 1, this end, which is negative, any type, if you follow it along the circuit, if you follow this diode, follow D1, we are saying this end here is negative. So if you follow it like that, with switch is closed, it will end at the negative terminal of the cell. or battery. Okay, similarly this end, which is the positive end, if you follow it like that along this path, you see it is also connected to the positive end. All right, so in other words, this diode is forward biased. Remember, in a forward biased mode, the any end of the diode should be connected to the negative terminal of the battery, then it is going to conduct. But if you look at diode number 2, you see that the any end, if you follow it like that, follow this path, the any end is connected to the P, or to the positive terminal of the battery. Therefore, this one may not conduct. So the answers to the questions, the question is saying state and explain the observation that would be made when switch S is closed. So lamp 1 is going to light because D1 is forward biased, hence allows current to flow through it to bulb L1. All right, so this will allow current to flow. But this one is in reverse. Since this one is reverse biased, so lamp 2 does not light because D2 is reverse biased, hence it resists the flow of current through it to lamp number 2. So in other words, lamp number 2 will not conduct, will not light, but lamp number 1 will light. It has to do with D1, diode 1 being forward biased, allowing current to flow through it, thereby lighting the lamp L1, and the D2 being reverse biased, thereby not allowing current to flow through, therefore lamp 2 will not light. All right, okay. Number 2, the circuit below has identical lamps L1 and L2, and D1 and D2, these are diodes. Explain what happens when S2 is open and the S1 is open and S2 is closed. All right, and then S1 is closed and S2 is open. Once again, follow the direction of connections. So diode 1 is connected, if you follow this path, is connected to positive of the cell. This one, the any end is connected to the positive side of the battery, while D2, if you follow that direction there, D2 right, so D2, if you follow the cathode here, then any end is connected to the negative. Okay, so which means that if we close S1, D2 only is going to, D2 conducts heavily, hence a short circuit is going to short circuit lamp 2, hence only lamp 1 is going to light brightly. Okay, so we are saying if we close here, close the switch 1, the condition is open switch 1. Okay, if we open switch 1 and close the switch 2, we close this. Okay, so current is going to flow through because the any end is connected to the negative of the battery, therefore it's going to conduct, but it will create, lamp 2 will create a short circuit, therefore current will not flow through it, and the current will only flow through L2. Therefore only lamp 2 or lamp 1 is going to light. So we are saying D2, take note, D2 is going to conduct heavily, hence short circuiting lamp 2. Take note of the connections. This diode as its n end connected to the negative, which means it's forward biased. So current will simply flow through the external part and not through lamp 2. So lamp 2 will not light. So in this case only L1, lamp 1 is going to light. Alright, if you look at D1, S1 connected, S1 closed, and the S2 open. You follow the connection of this diode to the cell. You see this is N type, which is connected to the positive. Therefore, it does not take up any current. So L1 and L2 lights dimly because they share the voltage, since they're just sharing the voltage, this one here. So the only circuit through which current is going to flow is this one here. Okay, and remember that voltage is shared among components in a circuit. So this end, this lower part here, will not conduct because of the wrong, I mean not the wrong, but the reverse bias connection of the diode to the battery. So only the only part that will have current flowing is the upper part, and remember these are in series, so bulbs connected in series will simply share the voltage supplied, the EMF supplied. You can go through this again and again, and in case you have any questions, don't hesitate to ask. Alright, so for now I would love to leave you with some work to do. You can go through the question in question number 3, work it out, follow the working out which we have given you down here, and also proceed to question number there are questions at the very end which I would like you to do and possibly share. Okay, I think I did not include those questions. So the only work you have to do is follow this question the way it has been solved, and in case you have any questions, don't hesitate to forward us your questions, or you can leave a comment in the comment section below. For the time being, thank you very much for listening, for being there. We are inspired by the fact that you're willing to learn. For now,